Yes, it was.
Are you ready to proceed?
Take it away, Paul.
Yes.
Hey, good evening, everybody, and happy last day of class. It's been a thrill to work with you all, and it's been a great learning experience. So for our project, the group wanted to decide, since I'm the most likely to die first. No, wait, that wasn't the decision. We decided to look at different causes of death by states in the United States and tried an attempt to make a prediction of what could be coming for us. Our group participants were Ian Lee, Navdeep Kaur, Paul Koo, myself, and Byron DeLeon. We used different libraries and dependencies and languages. We used Tableau Public, machine learning, and Python got the job done for us on this project. And basically, what our group is attempting to do is analyze the different causes of death that happened within 2020 through 2023 by state. And then the ultimate goal was to discover what the most likely causes of death would be for each state in 2024, based on the data that we gathered from the CDC. The data we used is linked below, and it's shared on our GitHub. The weekly provisional counts of death by state summarized by the CDC, so we felt our data source was rather accurate. At this point, I'm going to turn it over to Byron to talk about what the top 10 causes of death were among those years.
So we decided to narrow it down to 10 different types of causes of death. One of them being heart disease, which range of conditions that affect the heart. Some different forms of cancer. Most recently, a pandemic, which was the COVID-19 virus and its multiple variants that it had. Another will be respiratory disease, such as asthma and chronic obstruction pulmonary disease, and then cerebral vascular disease, which is a group of conditions affected by the blood vessels and the blood flow in the brain and spinal cord. The next one will be Alzheimer's disease, which is a degenerative disease of the nervous system. Then different forms of diabetes, which is a different form, whether being type 1, type 2, a metabolic disease involving inappropriately elevated blood and glucose levels. Then a inflammatory disease of the kidney. Then we have the influenza or common flu. And then number 10, we have other diseases that haven't been classified as of 2024.
Hey guys, so I'm going to go into the methodology of how we start the project in Python, the beginnings of approach to machine learning, and then exploring the data set. So the primary packages that we worked with were pandas, scikit-learn, NumPy, and I'm going to go a little bit more in depth about how we went about doing this. So we all know that, what data goes in is kind of like what we get out. So the value in the CDC data that we did was pretty clear. What I had to make sure was making sure that all the numbers were registered in the machine learning algorithm. So I had to change some of like the date time stuff. So we've done this before during the boot camp. We've changed the date time, extracted the years, month, day, and then I just converted it into different columns for those things so that the machine learning algorithm could read in those numbers properly. With handling the missing values, we did something called dummy coding. And so what we did was there were some things where we had to separate out the different states, and then I dummy coded them to kind of filter it out. You'll see it later on. And that was one-shot encoding, which we'll see later. And then we use scikit-learn to train split data set. So this is just kind of just a small, brief intro about going into using pandas. This is something that everyone knows, the pipe install, but not everyone knows this. So this is kind of a good way to get started. You import pandas, PD, then you import the data set, however you like to import it, pd.read_csv, and then the file. So this is where I want to slow it down a little bit and talk about my choice of which machine learning algorithm to use. And I was kind of inspired by what Justin was talking about in his real life training about using health data. And so I thought that the decision tree regressor would be a great way to start out. And I'll go into a little more detail about why we chose the decision tree. So a decision tree regressor is a non-parametric supervised learning algorithm which utilizes for both classification and regression tasks. And so to talk about, it would classify all the different diseases, classify all the states, and then it would use the regression to come up with the prediction. And to summarize what a non-parametric is, it's that a non-parametric is data that does not assume the shape of the data. And a supervised learning algorithm is when you have labeled data. So you use unsupervised when you don't have labeled data. But in this case, we had all the diseases labeled. And to even kind of fine tune and wrap it up even a little bit nicer into a bow, we use the grid search CV. And if you look at the bottom right over here, we have this decision tree regressor. And if you look above, perform grid search, where we did a grid search CV. And to kind of explain a little bit what that does, is what it does is it kind of does a testing of all the best case scenarios for your decision tree regression. And what it does, it finds the best parameters and it feeds it back into the next decision tree regressor. And so this is how we train the final decision tree for the best performance. So to go into the results and to explain a little bit more about exactly what we got, the accuracy, and to explain what we did. The first split training was all about all of the deaths. So what this did is if you look into the middle, you'll see that there's a column that says all cause, and right next to it says natural cause. And then it goes into all the different diseases as it keeps on going on down the columns. So all cause is all the deaths, whether it be natural cause of death or the diseases. So what we did, if you look at the X and Y, is we dropped the all cause to remove it from the X. And then for the Y to predict the all cause of death, we put it in as a Y. And then we trained that data, and what it gave us was an R squared of 0.968. So what's that saying is that our model is very, very accurate in predicting all the causes of death based on all the different columns that we have, natural cause, all the diseases. And I just want to take a step back and explain a little bit what the mean squared error is in this case, is how close is the prediction compared to the data. So what this is saying is the error rate of the mean squared is very low. So what it's basically saying that our accuracy was very high in regards to how close our prediction was to the data. And this is pretty similar with the root mean squared error. How is the average predicted values compared to the data? On average, it was only having an error of 0.21. So it had like a slight average error between all the different states, all the causes of death, all the diseases. And then we looked at the mean absolute error. And what that's saying is, what were the significant values in the data? What was the average difference between the predicted data and the end result, all deaths? So just to go into a little bit more detail here, we are explaining the results of the now filtered data of each individual state. And so I took the liberty of choosing my home state, New Jersey, as the filtered data. And then selecting the disease, I chose Alzheimer's disease, which I find was significant to me. And then I looked up the predictions of this for this training data set, and we got an R squared. For this particular one was an R squared of 0.66. So that prediction it did pretty well. R squared of 0.66 isn't perfect. It was not that high compared to like a 0.9, but 0.6, it's getting pretty good. And then with the other ones, without going into too much detail, mean squared, it's a little bit off, but it's kind of you can understand from the R squared that the mean absolute error, root mean squared error, and the mean squared error was showing just like kind of a natural sort of error rate. And then, so now this is the results of all the states before organizing. And so I just wanted to point out the combined predictions, just what it looks like in Python. You'll see that the R squared within the United States is very low because this is just all the United States together. But then if you look at our row, the 27,373, we look at Puerto Rico and we have with COVID a prediction accuracy R squared of 0.93, which is very, very accurate. So what this row is actually telling you is that for that particular week in Puerto Rico, you can find that the accuracy prediction for 2024 is highly, highly accurate during that week. So just to go a little bit more in even more detail about organizing the data, I'm going to run through how I did a for loop to loop through all the different states to filter all the different states to filter all the different diseases for the prediction of 2024. So I created an empty list to store all the predictions. And I'm just going to go through, basically, I append all the data from the different columns, from the different diseases, all the different states. I just put it into a for loop, which we learned in Python in one of the kind of first half of the data bootcamp. And then to finish it and to summarize the 2024 predictions, I do a group by. And then this is where it got a little bit tricky, is that when I used the group by, I had to use a df.pivot, which kind of basically turned all the columns on its side. And so what I did is I group by all the weeks predictions. I summed it all together for all the different states. So I summed all those weeks for each the state and all the diseases together. And so I put them and summed them. And then I basically did a like horizontal to vertical shift for the columns to do a prediction for all the different states and all the different diseases as columns. And then I set this out to export it, and I gave all the valuable data to Navdeep, who is up next.
Hello, everyone. So, Decoding Death, a dashboard that sheds lights on mortality trends across the United States. Let's start by looking at the national overview of death trends across the United States. As you can see on the map, each state is color-coded to represent the count of deaths by all causes. Notice the variations in mortality rates across different states. For instance, California with the highest and the Alaska with the lowest rates. This visualization helps us to identify regions with significant health changes. Coming to the dual axis chart provided a comparison of most deadly diseases, allowing us to see how they vary across different states. So understanding these variations can inform targeted health strategies and resource allocations to address regional health disparities. Moving on, let's take a closer look at the top 10 deadliest diseases nationwide. This bar chart illustrates the proportions of deaths attributed to each disease. So the heat map displays how the overall mortality rates have fluctuated over time. Understanding these patterns help us anticipate further like future healthcare needs and adapt preventive measures accordingly. Looking ahead, let's explore the forecasted death trends for the year 2024. The forecast line chart projects the expected trajectory of mortality rates based on the historical data and predictive models. So it shows that 6.7 million are going to die in 2024. Let's explore this dashboard more. If we go for a particular year like 2023, all the other sheets are going to be filtered based on that year. You can see the states, how many people die in that particular year in a particular state. And the two top states that are most affected in 2023 were the California and the Texas. And if we look for of which disease people most died of is Like if we can see in both of these states, the people died due to the disease of heart. And the top 10 diseases shows that the people in 2023 that mostly died of the top 10 diseases. If we select a particular state like Texas, in the states, it's going to show you the dual axis, like only for Texas in year 2023, and the top 10 diseases that are people most died of in year 2023 in the states of Texas. Okay, before we conclude, I would like to share how we can access the detailed dataset using this analysis. So displayed on the screen is an image with a direct link to the dataset. Feel free to explore the data further for your own research or analysis purposes and leverage it to gain deeper insights into mortality trends. So our next dashboard, we're gonna look for like the machine learning model predicted values dashboard. It features an interactive map, state selection drop down, and a dynamic visualizations reflecting predictions for the selected state. So if we go like, for instance, we select New Jersey from our drop down menu, the dashboard predicts that the heart disease will be the leading cause of death. Heart diseases remain a critical challenge in New Jersey. Now, switching to California, with the highest number of deaths in the last couple of years, we see a similar trend with the heart diseases topping the list. California's diverse population and health initiatives give us an unique insights in how such diseases can be managed on large scale. Moving on to Alaska, the scenario changes with cancer predicted to be the leading cause of the death in 2024. In summary, our dashboard offers a vital tool for predicting and preparing for health challenges state by state. We encourage everyone here to explore further and utilize these insights to craft more effective health policies.
Okay, so in summary, we use machine learning to decode and predict death. So we got our data from the CDC database. We cleaned the data, we modeled the data, and then we use the training model to get a prediction of the most likely death, what you're going to die of death. So the goal was to get an R squared of greater than 0.80, and we got an R squared of 0.968. And we took that data and we used Tableau to display our results. Okay, so here's the implications of how to use our data and where we think we can take it. Healthcare policy does not cross state lines for the most part. Each state has their own policies. So by analyzing the state-by-state mortality data, we can help policymakers and public health officials identify regions most in need of healthcare resources. This way, we are able to target, we have a targeted approach that allows for more efficient use of funds and manpower. So they can focus efforts where they are needed most to save lives. The dashboard highlights diseases with the highest mortality rates, providing a basis for developing targeted preventive measures. So by understanding these patterns, health departments can implement specific health programs, such as screening and education and other preventative health programs. So, so health challenges do not respect state boundaries. So this data encourages states to try to share data and share successful strategies combating common diseases. Collaborative efforts can lead to innovations in treatment and prevention to benefit a wider population. Okay, so today we've looked at trends in mortality across the US, and we identified key diseases and we try to forecast future trends. The dashboard serves to understand and react to these patterns. So in our call to action is for people in the healthcare industry who are involved in the planning and policy making to try to use this data to better health outcomes for the people of the US. So we'd like to, in our acknowledgements, we'd like to thank the developers of the used count libraries, our instructor, Justin, and our TA, Ricardo, and our past instructor, Rouge. Okay, now we open up to the questions.
Great work. Very well done. I could really see how this project can be really helpful in your portfolio and could garner a lot of interest from a wide variety of employers. I really, really enjoyed how you introduced a lot of transparency in your project. I think Ian mentioned it's healthcare, and a decision tree classifier might be a better approach than a more complicated model or one of the more black box models. And not only with that, but also with the Tableau dashboard as well, by adding that URL link that connects you to the original data source. That's another form of transparency. So you can really, trace the logic of your analysis all the way back to, the original data set. That's really awesome. I think I saw that you had, around 0.96 R squared, the coefficient of determination on the all-cause mortality. But then when you broke it down for individual diseases and individual states, it was a little bit less. Am I correct?
Yeah, you're correct, Justin.
And that makes sense too. If you think about it, just in terms of the data integrity, all-cause mortality, that's whether someone died or not, right? It doesn't matter what the disease was. Whereas when you start breaking it down by specific diseases or the cause of mortality, well, sometimes people have multiple conditions, right? And that's a little bit more subjective of the doctor and the, diagnosis that they did. So it does make sense that inherently there's going to be a little bit more variability, maybe, in terms of what doctor made the assessment, where the assessment was made. So and that makes sense. And I really like how the logic of your analysis was easy to trace. Just a suggestion is again, like other projects, this can be a 2-year project. It can be a 10-year project. It's always going to be super helpful to have a good idea or grasp on the things that are causing people to die, right? We all want to live longer, but we also want to save money and not pay more taxes than we need to when it comes to healthcare. So I could see how this could be a very valuable project. Is there any visuals outside of the Tableau dashboard that you guys were considering? Maybe something around how the decision tree made its decisions.
I was thinking about printing out what it looks like, the kind of the little cascading of the true false kind of thing. But I just thought that would be too big and I wouldn't really say anything because of how big it was going to be. I do hear you, Justin, about the economic portion, maybe with like financial, with like insurance and that kind of thing, which I think with more time, I think we could have added some sort of correlation data that maybe would provide even more financial insight into this venture that we went on. And there's another point that I was thinking about earlier, but it's not kind of fruition yet in my mind, but it's also something I've been thinking about.
Sure. And is there, can you think of any employers that would be interested in this type of analysis? I would bet that the CDC would have some interest to see what you did with their data.
Yeah, I was thinking about the CDC, like some government health stuff, and then like Johnson & Johnson for some example companies.
Yeah, I really liked about how, like, at first glance, when you think about a analysis that's predicting mortality, you think about improving the lives, improving the lifespan, actual health outcomes. But I really like how you guys called out the administration of healthcare, resource allocations. There's so much more that goes into it rather than the actual, physical makeup of someone's health. So I really like how you guys called that out. So I have no more questions. Well done, guys.
Hey, I'll just pick up where you left off, Justin. A really great presentation. Really surprising finds. I was really blown away by how much information you guys were able to deliver in such a short amount of time. And then overall, the flow of your presentation, I thought it was fabulous. The visualizations were appealing. Filters were functional. A lot of things you could just hover over and get some data points, which I thought was cool. One thing I would also note is that the public would also benefit from this analysis, right? Like if anybody has any pre-existing medical conditions or just wants to know where the best healthcare may be to, help them make an informed decision about their next move, it's something that can also be considered. So I guess the one question I have for the entire group is, was there anything about the analysis or research that surprised you all or any one of you during the project?
Dakota, I really want to jump on that vein. Yes, with that thought was actually how I kind of contrived this project in a way. Recently, I was like kind of thinking and contemplating about like why all these different types of ways that have affected people, and I thought that this project kind of would maybe even bring some closure to some families about like why or like what other people are going through regarding like Alzheimer's, cancer, all those kind of different diseases.
Oh, and also what surprised me was each state has their own policies and procedures. And also each insurance company has to have their own separate offices in each state to deal with all these policies and procedures.
Lots of red tape we're finding, right?
Yeah.
And just to add, if we can all agree on the truth, right, and the truth comes from analyses like yours, then some of the red tape hopefully can be reduced. And just a little bit of reduction, when you scale it across the entire country, it really goes a long way.
Well done, everyone. Thank you.
Thank you.
Good work.